All right, one of the new things we're going to talk about today, which is something that's kind of a common sense thing, you just have to hear it before you understand it, is how to determine the concentration of an ion in a compound. Okay? Does that make sense? Okay? No, not in calculus. Oh, it does. It does, yeah. We're going to talk about those on Thursday. All right, so here's what I'm talking about. So if I tell you, why is this? Oh, no. All right, so if you have this solution, what solution would this be? Okay, so I would have a NaCl. What state of matter? Aqueous, very good. So I need to put the AQ. And I have a concentration, right? Let's just pretend that it's 0.75 molar. Okay, do you agree that's the concentration for the entire solution? Then a question pops up and says, what is the concentration of the sodium ion? What? 8? Okay, so the entire concentration of the sodium chloride solution is 0.75. But I want to know, what is the concentration of just the sodium ion? Okay, how many of you would think it should be half? It should be half of the 0.75. Like the concentration of just the sodium ion. Well, isn't half of the solution half sodium ions? Well, why is the solution not half of the concentration? That's not how you do it. So here's how you do it. Okay? If you want to know the concentration of all of the ions in a certain compound, multiply the concentration of the solution by the subscript of the ions if asked about the molarity of a specific ion. This is a lot of points of multiple choice, and I think this actually came up in some of those worksheets I left for you last Friday, which we're going to work on Thursday. So again, it's really simple. So if I go back and I ask you, if this is a sodium chloride solution, what is the concentration of the sodium ion? 0.75. You multiply the concentration times the subscript. What is the subscript of the Na? 1. All right, so what is the concentration of the chloride ion? 0.75. All right. What if I take this, but I change this to Ag2 SO4, which would be silver sulfate? What would be the concentration of the sulfate ion? What about the silver ion? Why is it 1.25? Because 2, that's right, my bad, 1.5. That's what I was thinking. 1.5. So all you do is just double it. So for every 1 silver sulfate, how many silvers should you get out of it? You should get 2. So isn't that double the concentration? Does that make sense? Peyton, I'm needing you to be with me. For every 1 Ag2 SO4, how many silvers do you get out of it? You get 2. That's why for every 1, you get double the concentration. Does that make sense? Okay. All right, so again, it's super easy. It shouldn't be any more difficult than that. All right, so what is the concentration, let's just talk out loud, of the cobalt in the cobalt nitrate? 0.5. What is the concentration of the nitrate? 1. So how did I get it to be 1? For the nitrate, it's 1.0. There's 2 nitrates for every 1 compound. Okay. What about the concentration for the iron? 1 molar. All right. What about for the perchlorate? 3. Very good. Oh, it's that simple. It really is as easy as you're thinking it is. You take the subscript and multiply it times the concentration for that particular ion. No, it's pretty straightforward. Okay, so again, there's that. All right, so calculate the number of moles of chloride ions in 1.75 liters of a 1 times 10 to the negative third molar zinc chloride solution. Okay? What are they asking you for? What is the question asking you for specifically? What are they wanting to know? The moles of the chloride ion. All right, so here's the deal. So they've given us two things. They've given us volume, and they've given us concentration. Can you get moles from volume and concentration? Look up there in yellow. How would you do it? Moles equals molarity times liters. Now, one of these numbers isn't going to change, right? So the liters is 1.75 liters. But the problem is we need the concentration of what specific ion? The chloride ion. So, how do you know what the concentration of the chloride ion is? And this is really a typo. I'm going to kind of scratch this out. I don't know why I didn't change that, but it's 1 times 10 to the negative third. Yeah, I just moved the 3 to the other side. It's 1 times 10 to the negative third. Say that again. Okay. Why are you multiplying the concentration times 2? That's the chloride ion, right? So, what is... 0.00... Yeah, that's right. 0.002. Yeah, I didn't want to go too far. That's right. 0.002 molar. Okay? So then you would multiply those numbers. So this is when, if you have your calculator, that will be super beneficial. Which is 0.0035 moles of the chloride ion. So there's two things we need to talk about here. Number one, how do you get from moles from concentration and volume? How do you get from moles from concentration and volume? Multiply. This is a fact that you've got to have memorized. Okay? Then the question is, they want to know the chloride ion, but they gave you the zinc chloride. So you have to find the concentration of that ion. How do we find this 0.002? Multiply the concentration times the subscript of the ion. What if the question was changed and they said they don't want the zinc ion, they don't want the chloride ion, but they want the zinc ion? Would the math change? Yes. It wouldn't be 0.002. What would it be? 0.001. Does that make sense? How did I do it? I got you. All right, so let me show you what she's talking about. This is what I did in the packet. If you don't know what she's talking about, so I went moles equals molarity times liters. So I went 0.001 molar times 1.75 liters, and this gives me, what was the answer to that? And this is moles of ZnCl2. Okay. Can I get from moles of this to moles of the chloride ion? This is all you have to do. In 1 mole of ZnCl2, how many moles of Cl minus are there? There are 2 of them. So mathematically, what would you do to those numbers? Multiply, which gives you 0.0035, right? Are both answers the exact same? There should be no difference there. Does that make sense? Did that confuse anybody? Does this way make more sense or less sense? It's more obviously the answer, if that makes sense, because you show the conversion. I actually showed how I went from one to the other. Here, I did not really show how I got that 0.2, and that can be the confusing aspect of it. But that's when you just have to have the ion to concentration ratio. Okay? All right, there's that. All right, somebody read that first sentence for me. All right, pause right there. You said 9.82 grams, okay, of copper 2 chloride. Go ahead. Okay. All right, let's pause right there. Let's think about this for just a second. Do you agree that they're telling you that copper? I'm going to kind of throw a curveball at you. CuCl2 plus Al. They said a reaction occurs. So did this have to react? My first question, what type of reaction is this? Single. You produce the products. Figure out the products. Don't say it out loud. Did I already do that? Okay. But I want to make sure that you guys can do it. I want you to finish that reaction. This is a part of the chemistry that I kind of expect you guys to remember how to do. You obviously recognize that it's single replacement. I just hope that you remember how to complete the single replacement reaction. We're at the products in balance. I was fixing to ask you, does it say a solution of copper 2 chloride? All right, so I'm just going to throw this in there. So this is aqueous, and then it says a piece of aluminum. So what would you call that? Solid. Now, and it says a reaction occurs. How could you tell with your eyeballs? Color change, heat and light, bubbles, a solid precipitant, oxidation. Y'all keep working. Let me go look at something real quick. Okay, so we said this reaction occurs, but what would we have to really look at to see if this reaction would occur? The activity series, but I'm going to tell you this now and forever, that if we ever have a single replacement reaction in AP Chemistry, it will always work. And I'm almost sure that aluminum is above copper on the activity series, so that reaction should work. So what are we going to get as our products? And here's the tricky part that I'm quizzing you on. You've got Cu what? Solid plus AlCl3. That was the part that I wanted to see if got you or not. Why is it AlCl3? Very good. Al is a 3 plus. It's always going to be a 3 plus. So we've got our 2, 3, 6 rule going on. So I've got my 3 here. I've got my 2 here. Got my 2 here. And I've got my 3 there. So that's pretty much what's going on. So hopefully that makes a little bit more sense. And so what they tell you is you're starting out with 9.82 grams of this and enough water to make a 600 milliliter solution. Okay? And they throw it in and they say blah, 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 blah. And then the question is, what is the concentration of this stuff after it reacts? That does say morality, doesn't it? What is the molarity? I got the R and the L backwards. My bad. What is the morality? It is great. It is great. Somebody on your iPad real quick, or on your phone, look up the molar mass of copper 2 chloride for me, please. All right, well, that'll work. All right, so I've got 9.82 grams. So first of all, I don't even know why I'm doing this. So I've got to find the concentration first, right? So the degree I've got to get from copper 2 chloride to the chloride on the opposite side. Why am I going to the opposite side? Read the very last 4 words. After the reaction occurs. Now, when is after the reaction? A reactant or a product? So I've got to get to the products. So if I have something about my reactants, do you agree I have to get to my products? Okay? So the first thing I'm going to need to get, if they give me grams and they give me volume, and I know that these are 2 totally opposite things, but when we think about molarity, we think about what? Moles over liters. Are either of these 2 units given in the problem? No, but can you get to these 2 units from the units that are given? Yes. So I've got 9.8, what is it? 2 grams of CuCl2. And what is that in molar mass? 134.45. Okay, and that's how many moles? How many moles is that? I'm gonna do it a little bit different. 9.82 divided by 134.45 gives me 0.0730 moles. And so now I've got 0.0730 moles. And the volume was 600 what? Milliliters. So how many liters is that? 0.6 liters. So I'm going to divide that by 0.6. Ooh, that's not right. Which gives me 0.122 molar CuCl2. So I found the concentration of that copper 2 chloride solution. Right? Okay. So, everybody got that? You sure? I know. I know. Hold that thought. Hold that thought. All right. So now I'm going to come back over here and I'm going to look at this. And I now know that my concentration is 0.122 molar. Can I go from the molarity of one compound to the molarity of a different compound? How? Very good. I can go mole to mole, right? I know, but I'm just making sure everybody else is aware of that. So, I can go from moles of CuCl2. Actually, you know what? I don't necessarily have to go moles. What can I use? Can I actually use molarity? Molarity works the same way. Okay. Of CuCl2 to AlCl3. And then what is my mole to mole ratio or molar to molar ratio or liter to liter ratio of all of these? I know you don't need the liters, but you can use molarity. What is it? Okay, it's 2/3. Now here's the part where you got to pay attention because Peyton, you're fixing to ask me about this. You said, but I need what in the very end? Yeah, so the final question is what is the concentration of the chloride ion after the reaction? So do you agree I've gotten to the right compound? Okay, so now what I can do is in 1 molar of AlCl3, how many molars would you have of the chloride ion? 3 of them. So 3 molar of the Cl ion. And again, where does that come from? It just comes from the subscript. Yeah. So this first step is what we call the molar to molar. And where do those numbers come from? The coefficients. Okay? The last part is the molecule to ion ratio. So again, this is molecule to ion. Now, what does a molecule to ion mean? It's not really a molecule. It's really a compound. That's a bad word. I don't like molecule. I like compound. It's a compound to ion. And I'm going to add one more thing, just to make it hopefully a little bit clear. This is from your, can y'all see that color? Change it to white. No. Wasn't cool to do it back then. Who? Oh. No. She's lying to y'all. She is totally lying. She has the same degree I have. She's so lying to y'all. I'll ask her about that today. Hold on. All right, so again, I just want to point this out. Your molar to molar. Now notice, am I going to within the same compound or different compounds? Different compounds have to use coefficients. The same compound, you use the what? The subscripts. And I'm just trying to get from one of the ions, from the compound to one of the ions. And that's why I wrote that. That's exactly why I wrote that. So now, have the numbers become a lot simpler to work with? Yes, all right, so 1.22 times 2 times 3 equals divided by 3, which really you just have to double it because those two. So it is, would you say it was? No. 0.24. 0.243 molar chloride ions. Actually, in brackets, you want to put it in 2.2. What? Okay. How did it? Remind me how I did it. I didn't stop. I did the whole all one step. Okay. This to me makes it. To me it does because you're finding this part, and then once you find that, it's just mole to mole and then mole to mole for the ions. Again, either way works. And that's the thing about stoichiometry. There's really no one way to do it right every time. You can. There's two ways to skin a cat. So. Touche. All right, we're gonna skip that one. Move on to this. All right, so the preparation of a molar solution. How many grams of sodium chloride are needed to prepare 1.5 liters of a 0.5 molar NaCl solution? So this is an interesting part. This is an interesting question because it's a lab-based question. Because can you go with the digital scale and weigh out and mass out moles? No. So if you actually had to create 1.5 liters of a half molar sodium chloride solution, do you agree you would have to start with a certain mass of salt? Yeah. Well, they've given you two things. From those two things, can you work your way to grams? But what's the middle thing that you have to have? You've got to have moles first. All right, so let's start there. Yeah, do it by yourself. Yeah, I'll give you 2 minutes. All right, so here's the answer. So you're taking 1.5 liters and you're multiplying it times 0.5 molar, which again, molarity times liter gives you moles. Once you know the moles of sodium chloride, then you can then convert it to grams by multiplying it times the molar mass, which would have given you 43.8 grams of sodium chloride. So if I gave you a 1.5 liter volumetric flask or 1.5 liter Erlenmeyer flask, you could have taken 43.8 grams, put it in there, dissolved it, and then filled it up, and it would have been exactly a half molar concentration. Okay. So again, there's kind of one of those things. Last year, I gave the class a challenge to go to different restaurants around town and ask them when they make their sweet tea, how big of a jug they use and how much sugar they put in. And some of the concentrations were like over 5 and 6 molar sweet teas. It was absurd of how sweet some of them were. Okay. All right. So moving on. So here's the part that I want you to do, and I actually want you to try this one. If you haven't done this one, this is the important one, and I'm going to pause. I'm going to let you do this. I want you to go from start to finish. I want you to explain, when you see this word, and this is the important part, explain to me, if I had never done this before, how to make 500 milliliters of a 0.5 molar sodium nitrate solution, starting with solid sodium nitrate. This is kind of one of those questions that you may see in the future. So you may want to know exactly where to start and how to finish it. Okay, I'm going to give you just a few minutes. Do the math, and then explain how you prepare this solution. All right, so here's what we need to do. The first question is, explain. So you've got to use words to tell me how to make the solution, starting with solid sodium nitrate. So when it says solid, what unit are you going to be needing? You're going to be needing grams whenever it says solid. But how do you get from milliliters and molarity to grams? You got to find moles first. All right, so I've got to find moles, but what is the problem with one of the units? It's in milliliters. So what do? All right, so it's 0.5 liters times 0.5 molar, which gives me how many. I'm actually going to get off this page because it goes a lot slower. So moles equals 0.5 molarity times 0.5 liters, which gives me how many moles? 0. It's not 0.25? Doesn't sound right, but okay. Moles of NaNO3, and then we've got to get to grams. So in 1 mole there, would you say 58 or 85? 85.0 grams, which gives me how many grams specifically? 21.3 grams of NaNO3. Now, could you perform this lab? Okay, so here's what we got to do. How would you start this? Mass out 21.3 grams of NaNO3 and place Na. Now, I'm going to pause right here. So so the two things we did, we massed out. We talked about exactly how much, and we talked about exactly what. Those are two things. Do you agree that we would need to know those two things? How much and what? What if I just said mass out 21.3 grams? Of puppy dogs? I mean, of what? Okay. And place Na, what? 500 milliliter what? Volumetric. Because there are two different types of flask. I promise I'll slow down, Claire. I promise. Okay, I'm going to get it all written and I'll stop. So 500 milliliter volumetric. Kind of had that panic look. I was going too fast. Volumetric flask. Yes, sir. No. What did the question tell you? It said 500 milliliters. So if it would have said a liter, if it would have said 1.5 liters, I would have said a 1.5 liter flask. Bingo. Yes, sir. No, because because even though the flask says, even though it says a 500 milliliter volumetric flask, those flasks are labeled as exactly 500 liters and it has more room. So it makes sense. It's not exactly 500 milliliters and it'll be overflowing. It's graduated at 500 and has more room for overflow. Okay. All right. So placing a volumetric flask. Then what? Very good. Add enough. Keyword hot distilled H2O for what purpose? To dissolve, let's add to practically dissolve. Again, and that's kind of like I said, practically gives you some leeway because if you said completely dissolve, you could be swirling forever. Look it up, that's fine. Very good. That's the next key. Virtually? Go with whatever synonym, adjective, or descriptive term you would like to use. Practically is just the one that kind of flew out of my mouth. Ah, well done. But that could then take you forever. Okay. Then what? Mine's Thursday. No. Yeah, I'm teaching. That's my bash. All right, so again, this is how I would explain this. You're going to mass out 21.3 grams of sodium nitrate and place it in a 500 milliliter volumetric flask. Add enough hot distilled water to virtually, what else you say? You can say visibly, virtually, there, in whatever word besides completely, to dissolve all of the solid by swirling or stirring or shaking or whatever adjective. Then fill the flask to the 500 milliliter mark on the, actually I meant neck, not flask. And again, if you want to add some bonus information to make it even more perfect, you can say to create a 0.5 molar NaCl solution. Again, that's just some of that extra special stuff. To create a 0.5 molar NaCl solution. That's just making it even more exact. But whatever you prefer. You do feel smart? We're actually going to get you guys to do this soon. Okay. Because I want to do, once I cover dilutions on Thursday, we're going to start them today, but once I cover dilution, we're going to do a solution and a dilution. We're going to try to do a serial dilution as well, which you'll understand what serial means. No, you cannot eat it. Serial means in stages, multiple steps. You got it? Shh. I feel like I need to watch this show since I teach physics. I don't have a Netflix, so I don't care. All right, real quick, let's just talk about this one. Shh, let's just talk about this. Guys, to analyze the alcohol content of certain wine, a chemist needs a 1 liter of an aqueous 0.2 molar. What is that? Very good. Potassium dichromate solution. How much solid potassium dichromate must be weighed out? So how would you do this specifically? Just tell me, don't write it down. Hold on, let me pick on somebody. Chris, tell me what you would do. Yep. How much solid must be weighed out? How would you do it, Chris? Shh. James, help him out. Cody, help him out. Yeah, just tell me what I need to do to answer this question. Stop. I'm asking 3 people. I still don't have an answer. Stop it. Okay, James, go ahead. How? James? Chris? Cody? All right, very good. So we'll start there. So we've got moles. Let's change color. So we've got moles, which equals molarity times liters. Okay, and that'll give me a number. What's the number, Brandon? 0.2 mole. All right, James, Cody, or Chris? What's next? Very good. Brandon, what is the molar mass? Okay, which would give me how many grams? All right, 58.8 grams. So then I would take this 58.8 grams and I would put it in a, how big of a flask? A 1 liter volumetric flask. Put enough water in of hot distilled water to practically dissolve by swirling, and then that would create your solution. So again, that's just kind of throwing that at you. All right, so now let's talk about dilution. I promise we'll work on it. Okay. All right. Dilution. What is dilution? Stopped or started? Started or stopped watching? Stopped watching. So you didn't get any of this pre-stuff. We'll see how that goes. All right. So dilution is what? Lowering the concentration. That's the key. Now, listen. When we're dealing with dilution, we are diluting a solution. Okay, the way we do that is by really one of 2 ways. What's the easiest way? Adding water. Because what are you doing mathematically to the concentration? Okay, first of all, let's talk about this. Let's talk about the math. We're lowering the concentration, which is molarity, right? What is molarity mathematically? Moles over liters. Now, really, it's the moles of the solute divided the liters of the solvent. And that's something we don't talk a whole lot about, but is that true? So it's that solid being dissolved divided by the amount of the stuff dissolving it, right? So when I dilute something, you told me to add water. Which one of these is this affecting? The solvent. So if this number goes up, am I adding any more solid to it? So this number stays the same. So mathematically, when your denominator increases and your numerator stays the same, what has to happen to your concentration? It's got to go down. So that's how it's going to work. What is another way, but would be much harder to do? Very good. We would have to remove this stuff, which is impossible, right? So really, there's a way you could figure out how to do it by filtering, possibly, some way, but it's much, much more difficult to do it. So we're going to do dilution, sir. Exactly. Okay? So, preparing solutions by dilution. That's a fun way to talk about it. Guys, I'm not finished. We're still going to the bell rings. Often, your solution involves tomorrow.